professor at Stony Brook University, Stony Brook. He did his PhD from Goethe University, Frankfurt, Germany, on collective phenomena in the non-equilibrium quark-gluon plasma. However, his research interest includes phase structure of quantum chromodynamics, relativistic hydrodynamic simulations, non-equilibrium field theory, transport theory, nonlinear dynamics, plasma instabilities, and many more things related to these. He has worked as referee for many prestigious journals and also a member of numerous international advisory and review committee. So for his work in nuclear theory, for his extraordinary contributions to this high energy nuclear physics, he received the Zimani Medal in nuclear theory, and he also received many other awards. And he's also part of the JETSCAPE collaboration, who deals with this collaboration deals with the characterization of jets in a theoretical framework. So, well, that is it to introduce Dr. Schenke, and with all of the participants, I am also eager to listen from him about this topic, which is listed here as for this evening lecture as theoretical description of momentum anisotropies in small systems, which is getting more and more interest every day. Okay, so with this, I invite Dr. Schenke to start his lecture.
Okay, thank you very much. Thank you for the kind introduction, and to the organizers for the invitation. I'm very happy to be here. It was a very easy trip to India this time. Hopefully at some point, however, we can do this in person as well. So my topic is mostly focused on small system. I'm going to talk a bit also about heavy ion collisions. And I want to focus on something that we can learn about the initial state, namely really what the internal structure of the nucleus and the nucleon looks like at high energy. But first, I want to give you, just a few slide introduction about, what really the frameworks are that we are using. And as you are probably aware, really heavy ion collisions are quite a mess. A lot of stuff is produced, thousands of particles. Initially, things are out of equilibrium. So we have to come up with efficient methods to describe this. And what this article here on the slide says is more is different, meaning that, if you have a complex system out of many, many particles, it's not a good idea to just extrapolate from what you learned about a few particle systems, but you have to come up with a different way, namely effective theories to describe all these emergent phenomena that you have in a complex system of many particles. That includes phase transitions, critical phenomena, the hydrodynamic behavior, also gluon saturation, plasma instabilities, and so on. So here I want to focus in particular on two different effective theories of quantum chromodynamics. One is the color glass condensate, which is a good effective theory at high energy. So you can actually derive this from QCD in the right limit of high energy, where you also have high occupation numbers. And I come to that in the next slide. So this includes gluon saturation at a small longitude momentum fraction x. So that's the momentum fraction of a parton in a nucleon or a nucleus of the longitude momentum. And at transverse momenta that are smaller than a certain scale, that's an emergent scale, that's the so-called saturation scale, QS. And this saturation scale is typically much larger than lambda QCD. So typically, you think of QS on the order of 1 GeV, where lambda QCD is maybe like 0.2 GeV, something like that. And then the idea is that you can treat things systematically in a perturbative way, namely that alpha S of at the scale QS is small enough to do this. This we use to compute initial conditions for heavy ion collisions. And the other effective theory is going to be relativistic hydrodynamics. So there we can use hydrodynamics to actually compute the final state in heavy ion collisions, where, and this is effective because we're kind of only interested in the long wavelength modes of the system. So let me go into a little bit more detail on the first one. That's the effective theory, the color glass condensate. And this tells us, first of all, what is colliding. So when we collide two heavy ions at high energy, from QCD and also from experiment, we know it's mostly gluons. So if you're looking at the proton distribution function that are shown here as a function of this longitudinal momentum function x, then you see you have some valence quarks distributions for up and down quarks. They peak mainly around, 1/3 of the longitudinal momentum because there's 3 of them. But then it's not quite at 1/3, it's a bit lower, and the rest is in the C quarks and in the gluons. And you see the gluons are here the highest, and they keep growing as we go into smaller and smaller x, so smaller and smaller momentum fraction. And the x's we probe at mid rapidity at both RIC and LHC are in this region down here where really the gluons dominate. So our first approximation is to just include the gluons. That's not a perfect approximation. You see the C quarks should matter too, but that's what we do for simplicity. We're probing this X region that's relevant. We have included, as I said, gluon saturations for transverse momenta of these same gluons below the QS scale. And because the occupation number goes like 1 over the strong coupling, 1 over alpha S, and alpha S is small as we evaluate it at the saturation scale, we have a large occupation number. And this allows for a classical description. So we can neglect the quantum effects to a certain degree, at least to first approximation, because there's a lot of stuff. So when you have a lot of stuff, you usually don't care about the quantum effects. Usually we can also include the leading quantum corrections though, which are included by the small x evolution equations like Jim-Walk or an approximation of that, which is the BK equation. This is a review. You can look at all about the CGC. This is a very, very short introduction here. But this is what we do there. And we implement this, for example, in the IP-Glasma model. So IP stands for impact parameter. That means it's impact parameter dependent. A lot of older Glasma models were not impact parameter dependent. They just used a homogeneous nucleus. But here, this is the important part because we want this geometric structure that is important in heavy ion collisions for computing and momentum anisotropies, for example. Now, as I said, the particle production is governed by the Young-Mills equations. So first, we have to determine what do these incoming nuclei look like. We need to determine the gluon fields inside of them. For that, we sample first nucleon positions. So you can see these little dots that are in one nucleus, the nucleons. Then we can either directly sample color charges inside these nucleons, or we also include a substructure, and I will get into details on that. And this is actually constrained, like what the structure looks like from deeply inelastic scattering at HERA. So if we look at diffractive vector meson production, for example, in electron-proton collisions, that is sensitive to what the proton looks like and how much it fluctuates. And this information we put in here as well. And that's using this IP-set model, which is also basically the basis of the IP-Glasma model and contains the geometry there. So once we've constructed this color charge distribution, we can solve the Young-Mills equations, which is just this here. So it looks like the Maxwell equations. It's just, I emphasize that this is in SU3 by this commutator. So there's some color structure in there. And it has this current J nu on the right-hand side, right? And this is the current that comes from just having these color charge distribution moving at the speed of light. So that's this current. And we have two of them, one coming from the left, one coming from the right. And then eventually they collide. And there's, for a long time, it's known how to solve for the gluon fields after the collision. And the solution is shown here. So the transverse components of the gluon fields are just the sum of the incoming ones. And there's a longitudinal or space-time rapidity component, which is just computed from the commutator of those two. I won't go into the detail how to derive this, but it's been known for a long time. And numerically, we can also solve this then. This gives us the initial energy momentum tensor. which is shown here, and has different components. It has longitudinal transverse components. Essentially, it has electric field and magnetic field components in the different directions. What's shown here is an animation, will be an animation like this, of the energy density, how it evolves over time. On the right-hand side here, I hope this is not covered too much. So we have the time evolution of these different components in the different colors. You see, initially, we only have longitudinal components of the fields, and the transverse components only have to build up, and eventually there's sort of an equipartition between the distribution among these components, and everything's dropping like 1 over tau because we have this longitudinal expansion. So this is what happens in the Young-Mills evolution, and eventually we want to plug this into the hydrodynamic evolution. And hydrodynamics is what follows next. So you can then take this energy momentum tensor at a certain time after some Young-Mills evolution and put it as an initial condition into your hydrodynamic evolution. This is more efficient. Doing basically the whole heavy ion collision, you may ask, could I do this in the Young-Mills evolution the whole time? That's difficult. So these simulations were in 2+1 dimensions. It was just a Bjoern expansion. We are missing some physics if we do that. So we're missing in the 3D, what we would have in 3D, namely, for example, plasma instabilities and thermalization, which may or may not happen, but some isotopization is expected. But it seems like we're still missing something. And also at late times, we would think we need quark degrees of freedom, et cetera, et cetera. So it's much easier, as I said in the beginning, to use another effective theory, namely the relativistic hydrodynamics, to describe this stage. So the basic equations of hydrodynamics are just energy momentum conservation. So this is the relativistic way of writing this, d mu t mu equals 0. So this is the energy momentum tensor, different components. And you can expand this into these more familiar terms, namely energy density, pressure, flow velocity with 4 different components. That's just a 4 velocity. And you have a metric tensor, and you have viscous corrections. In addition to solving this equation, you also have constituent equations for the evolution of this pi mu nu, which includes the shear viscous corrections as well as bulk viscous corrections, and also possibly heat conductivity and higher order transport coefficients will appear depending on your level of expansion that you're doing. So if you do second order hydrodynamics, you'll have some more coefficients than in first order. Then finally, to close the set of equations that comes out of here, you need a relation between the pressure and the energy density, P of epsilon, which is the so-called equation of state, that you can get from QCD in principle. So you can get that from actual lattice QCD calculations. So you put the actual QCD, including all the quantum effects, on a computer, and you can compute in a thermal system that's static, you can compute this relation. And that's what you take as input. But we have to couple this to a hadron gas equation of state at lower temperatures in order to be able to then match eventually to an actual hadron gas and sample particles. And in the end, maybe plug this into some hadronic rescattering like UrQMD, and then compare to data. For now, I just want to show you what this looks like. So this is an image of contours of constant temperature this is actually a gold collisions at 200 GeV. The duration overall is about 10 Fermi. And this is the evolution, what it looks like. So this is now in T and Z coordinates. So you see, and it's a little bit tilted. And you see how this evolves. You see it evolves, this temperature drops much more slowly in these parts that move at a very high velocity. That's just a time dilation effect. Otherwise, this is essentially a boost invariant calculation. It just doesn't look boost invariant because I have changed the coordinates to actually T and Z coordinates. If you plot this in tau eta coordinates, it would look the same at every eta. But if you convert again to TZ, you see this time dilation effect, which is kind of interesting. I want to show you another animation that you get. And in this case, it's showing the effect of the shear viscosity. here you have three different initial states. Now this is in a transverse plane. So imagine the beam would go into the screen and out of the screen, and they collide such that the reaction plane is in the screen. So this is the transverse plane here, and they're all the same initial condition. And I start the hydrodynamic evolution, and you see the difference between the different values of eta over S, shear viscosity over entropy density ratio. If you have no viscosity, you see these really sharp structures. If you have viscosity, it's starting to be blurred out, right? The viscosity is a diffusion effect, and it looks exactly like what you would expect from a diffusion. These fine structures are smeared out. And if you increase the viscosity even more, this effect is even greater. So it looks like you would expect. And now I want to get to what we all put together now and what our hybrid framework consists of. So as I said, the initial state will be this IP-Glasma based on the color glass condensate. Then we switch, so we take the whole T mu, the whole energy momentum tensor, and move that into the hydrodynamics at a given time. Here we choose, for the most results I'll show, 0.4 Fermi. There's an input of the equation of state from lattice QCD that I also mentioned that goes into the hydrodynamics. And then at a temperature of roughly 145 MeV, we switch, we find a surface of that temperature in the hydrodynamic calculation, and then plug this into UrQMD for the hadrons that we sample from that surface to further scatter and resonances to decay, etc. And then the final particle spectra, they will be averaged over events, and then we can compare to experiment. In detail, this is described in a fairly recent paper where we put all this together, which is called Running the Gamut of High Energy Collisions. I thought that was fitting because we're looking at really the whole range of energies and system sizes, both at RIC and LHC, but also because we're using the hydrodynamic called music. This is a term coming from the music field, so this kind of made sense. And as I said, I want to emphasize again, we exactly match the T mu from when we're switching from one part to the other. So both here on this red arrow and here as well. Before I show you all these results that we get from that, I want to focus on the initial state geometry, because that turns out to be an important aspect. And here I'm showing you something completely different in some sense. So this is what I mentioned before, this HERA data on the diffractive projection of J size in electron-proton collisions. I don't want to go into too much detail to explain this, but two things to point out in this plot is we are showing on the one hand, these black solid points is the coherent cross-section. So that's the cross-section you get if the proton that you're hitting with the electron does not break up. And the shape of this, so this is plotted as a function of the transverse momentum transfer squared, essentially. So basically the transverse momentum that the J psi has in the end. And this is the cross-section as a function of that. And the slope of this is sensitive really to the size of the proton, of the target. So if you have a flatter curve here, that means your proton is smaller because the actual size is going to be a Fourier conjugate of this momentum transfer. And if it's a steeper, if it was a steeper slope, that would imply that the proton is actually bigger. So this slope here tells you something about how big the target is, how big the proton is on average. Now the incoherent cross-section, that's these open points and the red curves, that is actually sensitive to the variance of the scattering amplitude. So that's sensitive to how much event by event fluctuations do we have. And this is, for example, sensitive to how much the geometry of the proton fluctuates. And this result here, this dashed curve, is what we get if we just include these color charge fluctuations. So that's sort of just some local color charges in an otherwise smooth proton. If we only include that, we get an incoherent cross-section that is basically an order of magnitude smaller than these open points, which is the data. And that's because we don't have enough fluctuations in that case. So what we did is to include an additional degree of fluctuations by including sort of a substructure of the nucleon, by including, in this case, 3 hotspots, just sort of motivated by having 3 valence quarks around which we think the gluons could be situated. And then event by event, the positions of these hotspots and also the normalization of how many gluons are in such a hotspot, we let that fluctuate. And when we do that, we get the solid curve, the solid red curve. So this data allows us to sort of learn about what does the proton look like and how much does its geometry fluctuate. And that information then we take and put it into the calculation for the heavy ion collisions, also the small system collisions like proton-proton or proton-lead collisions. So this is an example. If you take a round, what we call a round proton, it's not quite round because we have these color charge fluctuations on top, but it's pretty round. And if we use the substructure of 3 hotspots, then we get it, for example, a configuration that looks like this. And that makes a difference in these proton-lead collisions. So this is a comparison of this calculation with Ali's data. And we show what we get when we use for V2. So this is V22 as a function of the charge particle multiplicity. And we show what we get if we use a round proton. That's the red curve. So that's under this configuration. It's not 0 because we have a little bit of a shape and an eccentricity. And we show what we get if we use the substructure. That's the black curve. And you see it's a huge difference in the V2. We deviate somewhat from the data still, but we're doing much better when we include the substructure of the proton, which dominates in our model, dominates the shape. And I'll get to that. For V3, it's similar. We're still underestimating the V3. I should say we didn't tune anything else in the model. So the model was basically tuned just to heavy ion collisions at RIC energies. So everything is fixed from that. And here we're just changing the substructure at LHC P-lead collisions. So if one did a better, more sophisticated fit, I think one could do better. But one must also see that these are already very low multiplicities, kind of down here, especially here where we start deviating. So we may not expect perfect agreement, but it looks like the substructure is really needed to describe this data. And so I mentioned this briefly. So really the shape of the interaction region, so the shape of the energy density that we deposit in the proton-lead collision is really dominated in our model by the shape of the proton. So it's like punching a hole in a wall that has the shape of the proton. And that's illustrated here. So the color map is the energy density distribution that we have in the proton-lead collision as an initial condition. And the contours are a measure of the gluon density in the proton that we used in this collision. So you see where this proton has hotspots. We also get hotspots in the distribution here. So this really indicates that in our case, the lead is sort of just a screen, more or less flat. It also has some fluctuations in it, but the main shape of the interaction is dominated by the proton shape. Now, I was arguing, okay, to describe this data, we need the substructure. But then you may say, well, what about these other models that came out, 2013 already or 2017 that said, well, we just use a Monte Carlo Glauber model and we can describe the data. And we can describe the data pretty well without any substructure, right? Let me just briefly address I just saw a question. So what are these hotspots exactly? So the hotspots, what we model is just sort of 3 Gaussian hotspots. And it's just motivated by the fact that we think we have some large X structure in a proton. So the large X structure consists of the 3 valence quarks. It may also consist of additional large X gluons that have been emitted. So the number 3 is not a fixed number. It could be more hotspots that are relevant, or that number could even fluctuate as well. Here we just fixed it to 3. So it's just sort of the hotspots we think emerge from having a fluctuating large X structure around which then the small X structure evolves, for example, with the Jim-Wark evolution. And so gluons then will mainly be emitted around these large X degrees of freedom, which then looking at the smaller X will result in sort of a lumpy structure inside the proton. So that's what these hotspots are supposed to model. I hope this further explains this. So now back to these models, they don't have the substructure, they only have nucleons, but they do well in proton-lead collisions, right? And the reason is they're using a different model for the initial state. And the question is that model enough, right? And so what does it look like in that model? Now here I have two examples for the same nucleon configurations in the proton and in the lead. So the proton obviously is just one nucleon. And in the lead, we have some distribution of protons and neutrons that are these circles here. And if you look closely, they are the same in picture A and picture B. If I take these same configurations and then I use a Monte Carlo Glauber model, which uses the thickness functions. So thickness function essentially is just the density integrated over the longitudinal direction. So TA is the thickness function of the proton, TB can be that of the lead. And then we find wounded nucleons just by sort of the standard method in a Monte Carlo Glauber model. And then for each wounded nucleon, right, we add some Gaussian density, right? That's what's been done here. And we do this in a way where we just add the thickness functions. In our model, right, I showed you it's really, you compute this Yang-Mills equation, etc. So it will be really dominated by the proton shape. And if you actually work this out, you will find that this is more like having TA times TB. So instead of the sum, you have the product, which gives you the energy density in the IP-Glasma model. So very different, and they result in very different structures if you only include nucleons. And the question is, which one is the better one? Which one is the right one, right? So how should the energy deposition go? So there's many arguments for that this product to some power, which may be a square root or something else, is preferred. So there's been a lot of Bayesian analyses that have been done. So it's really a sophisticated way of constraining your parameters. And there's a TRENTo model, which essentially has a range of possible combinations of TA and TB, including the sum, but including also a square root. And every Bayesian analysis that I have seen in heavy ion collisions prefers the square root, TA times TB, to the sum. This model does not include the simple product, actually. So the closest we can get to a product is really this square root expression. From theory calculations, we also see something that looks like, more like a product. So ADS-CFT-based calculations find such a relation, which have more of a product in there to some power. IP-Glasma, as I said, gets the TA times TB for the energy density. And TA plus TB is also disfavored by the centrality dependence of V2 in heavy ion collisions, which was shown in this paper. So there's many arguments for why this TA plus TB is not a good description. Even though it works well for these VNs, the V2 and V3 in proton lead or proton gold collisions, for example. However, if we use the TA times TB like prescription, we get just too small eccentricities and we need these subnucleon fluctuations. So this would be my argument, sort of going through the string of arguments that there's a good indication, not just from HERA data, but also from heavy ion and small system collisions, that we need the substructure of the nucleons. Now, assuming, well, we don't have to assume that we have the substructure. So first of all, we want to see, do actually these different models, all these different Bayesian analyses, for example, actually agree on the size of a nucleon. So what we did in our model, we assumed a 2D Gaussian for the nucleon. So this W is the width of that Gaussian. And we found with the HERA data, actually, that the width of this should be 0.4 Fermi. So this is a bit smaller than the charge radius of a proton, but it's compatible with the gluonic radius, which is really what dominates here. The gluons dominate the energy density that we are interested in. So this is not unreasonable. And we also, in our case, used the subnucleon hotspots with a width of 0.11 Fermi, which is pretty small. So these are just three blobs with this size, which are distributed, whose centers in our case are distributed with this Gaussian. So on average, we will have something like a Gaussian with the size of the sum of this W plus WQ. Similar values of W were found in the past, actually. So in older models, different models, people got something like 0.4 or 0.5 Fermi for this width. But some recent Bayesian analyses of heavy ion data find a lot larger values. So if you look at papers from 2019 or even 2021 for two different groups, JETSCAPE included, you find a W of almost a Fermi. So this will lead to very different looking systems. So here I took a figure from Giuliano Giacalone, who compiled these. And so he plotted what the initial density distribution looks like for these different parameters found in all these different papers. And you see, you have some very smooth configurations, like in this TRENTo from 2019 or JETSCAPE. That's the ones with a very large W. And you have much more choppy configuration. So the older TRENTo or the also the TRENTo from 2018 and in particular the IP-Glasma, right, with our really small hotspots, that looks very lumpy. So what does the system look like initially? Does it look like this, or does it look like a very, very smooth blob? And you may ask also, how can I describe the V2 and V3 the same way if I have this versus this, right? Now, the answer is easy in one way. So you compensate that by other parameters. For example, the value of the viscosity. It will be different in these different models. And also there's some more complicated things like, some of these models have some free streaming phase, which makes things smoother. Again, for example, this will smooth out before it goes into the hydrodynamics, etc. So there's some complicated structure, but the main simple answer is really you can compensate for that with other parameters, which is bad because then you cannot constrain either one. So the question is, can we actually pin down the size of these nucleons and the viscosities, for example, individually, right? Is there an observable that has not been taken into account, in particular in these Bayesian analyses, that can do that? And the answer is yes, there is. It turns out actually that the correlation of mean PT with V2 is a very powerful quantity to do that. So we can define this correlation of the fluctuation in V2, for example, so n equals 2, and the fluctuation in the mean transverse momentum. So these brackets here are supposed to indicate the mean PT in a given event, right? And then these other brackets are the event averages. And these hats on top of these deltas mean that we subtract the variation that comes from fluctuation in the multiplicity. So it's basically just like fixing the multiplicity. Experimentally, you would just take very fine, very small bins in multiplicity to do this. And so this just measures the normalized correlation between the V2 and the mean PT. And here's a busy plot that shows that. And that's actually very recent ALICE data shown here in these points for this row correlator for V2 squared and mean PT and the one for V3 squared and mean PT. And there's also some ATLAS data shown. The curves should be compared to the ALICE data because it uses the same PT cut, and there is actually some dependence on the PT cut. And this is now lead-lead collisions, actually. So in lead-lead collisions, we also have sensitivity to the size of the nucleon, which is shown by these different curves. So the blue curve is what we get in our standard IP-Glasma calculation, which is this is this W of 0.4 Fermi and the WQ, which is the hotspot size of 0.11 Fermi. And for simplicity, the other curves don't include the substructure, but where we just vary the size of a more or less smooth nucleon in the IP-Glasma model as well. So we just turn off the substructure and we increase gradually the size of the nucleon. So going from green of 0.4 to purple 0.8 and gray 1.2 Fermi. And you see this correlator changes quite a bit when you change the size, and it even changes sign as we go to larger centralities. We show also this yellow curve, which is the same as the gray, except we reduced the viscosity a lot. So we actually turned off the bulk viscosity and shows a much smaller shear viscosity. And it shows that it does not depend too strongly on viscosity, but mostly depend, especially where it turns negative, it mostly depends on the size of this W. And the same is true for V3 on the right. Here actually, the viscosity you see doesn't have any effect. But the size of the nucleon has a large effect. You see a sign change in some case, which the data doesn't show. So the data is actually quite compatible, at least for the most part, with the smaller size W. And the red curve here is the result from JETSCAPE, just a predictor for this. So it's an initial state predictor for this quantity, which has this large, really large nucleon size, relatively. And you see there, we see the sign change, which is not there in the data. And that's the reason for that is that JETSCAPE used this large W. At least that's what we find by this study. If you were to make this W smaller, you will get the sign change at a larger value of centrality, or you won't even get one at all if you have the substructure in there. So this is a powerful observable, and it looks like we will be able, when using it in Bayesian analyses, to really constrain much better both the W, or the size of the nucleon, and the shear viscosity, for example, and the bulk viscosity as well. So I want to show a few results from the model, just to recap what we use for shear and bulk viscosity. Shear viscosity we just fixed to constant 0.12, and the bulk viscosity we use one that is peaked around so the pseudocritical temperature. And we need this sort of large value in comparison to other calculations because we have this smaller substructure, so it has to compensate for the additional kind of transverse pressure gradients we get from the smaller structure by including this larger bulk viscosity. So here's just some results that I could have shown earlier because it's a much simpler observable than what we looked at so far. But this is just V2 and V3 from two particle correlations. And we show them in different systems, here comparing to ALICE data in lead-lead, xenon-xenon, proton-lead, proton-proton collisions. And you see for the large system, this works extremely well. For smaller systems, P-lead, we underestimate a little bit, as you had seen. But for PP, we kind of fail. We're really pushing it here, and we haven't really tuned or tried to tune in particular the PP. So the tune was mainly done at RIC data actually, and the energy dependence is a prediction of the model. We also have some predictions for oxygen-oxygen collisions in green, and both for V2 on the left and V3 on the right. Let me move on to V24. So there's 4 particle cumulants. Again, this works even better, I would say. Looking here on the left at RIC data, the D-gold, we don't seem to describe really this dependence here on multiplicity, but there may be non-flow issues coming in when we get down to just having 2, 3, 4, or 5 particles, excuse me, for per unit rapidity. On the right is LHC data. We underestimate a little bit the xenon-xenon for the V3. Also in this region, a little bit the lead-lead, but overall it's good agreement, and even the P-lead, gets close here, and there's some prediction for oxygen-oxygen as well. The PT dependence, transverse momentum dependence of V2 is shown here on the left as a function. Well, sorry, on the left is a function of n, so it's V2, V3, V4, and V5. This works fairly well. There's a little underestimation here at low, but if you take at low PT, but if you take the error bar seriously, it's not bad at all. And if we and then on the right hand side, we have just a different centrality. So this is central collisions on the left, and this is more peripheral collisions on the right. Here we do underestimate at small PT and overestimate somewhat at large PT. Cumulant ratios, they are sensitive to the degree of fluctuation. So again, this is an important measure that's sensitive to the size of the nucleons as well. And in the IP-Glasma model with our substructure, we do a really good job in lead collisions to describe the data. That's this ratio of V24 over V22 as a function of multiplicity. Xenon. I believe there's data now. No, I'm not sure. It wasn't in this plot yet. So this was a prediction at that point. There's some oxygen description, prediction, and some p-lead result, which has really large error bars. So we need a lot more statistics than we have to do better here. And on the right-hand side, we have even V26 over V24, which again agrees extremely well with the data. So it looks like the level of fluctuations we have is well described. Now I want to say a few words about the RIC system scan. So there was an idea of really engineering the geometry of a small system by forcing the system to have one hotspot, mainly two hotspots or three hotspots on the level of the nucleons. So that's done by using either a proton projectile, a deuteron, which has two nucleons, or a helium-3 nucleon, which has three nucleons. So the simple model expectation from a Glauber model is that in the deuteron gold and helium-3 gold V2 epsilon 2, that's the ellipticity of the system, is much larger than that in proton gold, which just has one round, mostly round hotspot. At least if you assume that there's not much substructure in the nucleon. And for the epsilon 3, you expect that the system with three hotspots has a larger epsilon 3 than the other two. And the data, which is shown on the right, confirmed this expectation. So Phoenix measured this, and it was published in Nature Physics, that the V2 is larger in in deuteron gold and helium-3 gold compared to proton gold, like this image here has expected. And for the V3, it looks like, again, this expectation, namely that the helium-3 gold has a larger V3 than the other two. So that looked all nice. Our calculation, again, not really tuned to this data, but had been tuned to gold data, looks similar for V2. So we see larger V2 in deuteron gold and helium-3 gold compared to proton gold, even with the substructure that we do have here. We overshoot the data a bit in all of them. So that's a bit of a discrepancy. But if you look at the V3, it looks like, well, the V3s are not too different in the calculation between helium-3 and the other two. Maybe a little bit larger for helium-3, but not as much as the data, right? The data shows a much cleaner difference. Then came the star data that was shown at Quark Matter 2019. And we see that the star data agrees pretty well with the Phoenix data for V2, but for V3, it's larger in proton gold and deuteron gold. And actually our prediction lies very close to the star data in this case. There was actually a task force instated to figure out where these differences between the experiments came from. We've found that Phoenix sees really large changes in V3 when changing the pseudo-rapidity ranges that are used. So what's happening is that, and took a slide here from Prithvish Tribady, that the results that Phoenix gets they remove non-flow by using large rapidity gaps. So the standard result here is using different detectors. And if they use different combinations of detectors, they get much different results. So they say, well, if we use these different combinations, we increase the non-flow. So this should not be trusted as much as the original one, which has the least non-flow. That's probably true, but I think there's another reason, right? That actually the V2 and the V3, or the epsilon 2 and epsilon 3 in themselves in the initial state change as a function of rapidity. And so this is an argument for not really comparing the boost invariant calculations that we're doing to measurements that really use large rapidity gaps. STAR is measuring everything close to mid rapidity, and they subtract the non-flow differently. And there we kind of agree with the overall trends that they see, right? So this is somewhat of a warning of using these boost invariant calculations. That includes ours, to compare to data that use large rapidity gaps, especially in these small systems where we have probably a larger decorrelation of the geometry, for example, with rapidity than we have it in heavy ion collisions. So also these results from Sonic and IEBE Vishnu that were shown in this Nature paper, they are boost invariant, and they're comparing this here to measurements that have large rapidity gaps. So this is a bit of a problem, and I think we have to do better on the theory side. We need to include these rapidity dependencies. So I'm already running late on time, so I want to just mention one more thing, namely the origins of this momentum anisotropy. So in heavy ions, it's pretty clear that the momentum anisotropy we measure is really coming from a response to the initial geometry, right? So we've seen this now a couple of times. What we put in there really determines what comes out. And however, there's another source of anisotropy which could be important in the small systems, namely that the initial momentum distribution is already anisotropic, in particular in the color glass condensate. It predicts basically a particle production without final state effect that already has some anisotropy. And the reason for that is the local anisotropies you have in the color field distribution. You have local density gradients in these color field distributions. And you also will have quantum interference effects, which can all cause an anisotropic momentum distribution of the produced gluons in this case. So when comparing just models with only the geometry response, so only these final state effects, as I've shown you before, these work pretty well describing this data. If you only include the initial momentum anisotropy, it does not describe the data. It actually has the wrong trend, both in PT here, as shown, but also in multiplicity dependence, so centrality dependence. Just by itself, this won't describe the data. However, these effects are there. And the question is, when do they become important? When should we be able to see them? And here, we just looked at this sort of in an academic way, only in the simulation. So we looked at the Pearson coefficient between the final V2 that comes out of the calculation and an initial state measure, either the eccentricity, so the shape of the geometry, or we put in a measure of the momentum anisotropy, which is shown here, this epsilon p, which is just given by this expression using the T mu nu. And we see that as we go to very high multiplicities in gold-gold collisions, right, the correlation between the geometry measure and the final V2 is basically 1. So it's just all coming from this geometry effect, and the correlation between this initial state and momentum anisotropy and the final V2 is 0. So nothing of that survives. But as you go down the multiplicity, especially now when you switch to deuteron gold collisions and you go down to very low multiplicities, this correlation goes down, and the correlation of the initial set momentum anisotropy with the final V2 goes up. It becomes pretty large. But you have to go down to very, very small numbers of multiplicity to see that. And again, experimentally, one might be able to see this by, again, looking at this correlation between V2 and the mean PT. So I've already explained this correlator, so I don't have to go through this again. But there's some expectations we have for this correlator, depending on where this momentum anisotropy comes from. If it's a geometric effect, we expect the following in a small system. So if you have a larger system, system A here, then the pressure gradients, and this is all at fixed multiplicity again. So a larger system at fixed multiplicity will have smaller pressure gradients than a smaller system. So we expect the mean PT in this system to be smaller than in this system. So this is this line here. But in a small system, if we have a more extended size, then it's more likely that we can achieve a larger eccentricity. While if we put all these circles on top of each other, make it really, really small, the eccentricity will automatically become smaller. So the eccentricity here will be larger, but the mean PT will be smaller. So this leads to an anti-correlation of mean PT and the V2, or the eccentricity in this case. So the prediction for this correlator from the geometric picture is that it's negative. In the initial state, we expect the opposite, actually. So if we have these color charge domains, right, which is sort of a cartoon version of, you know, these color correlations that we can have in the initial state, then we have a larger system here and a smaller here. And for this argument, I want to assume that the mean PT is still driven by the size of the system, so the geometric effect. So that, again, pressure gradients would be larger here in B than in A. And so the mean PT of A would be smaller than mean PT of B. But if the anisotropy comes now not from the geometry, but from the initial state, then because we have more domains here and production from different domains is not correlated, only particles produced from the same domain will be color correlated, then the eccentricity, or sorry, I should say the momentum anisotropy here from case A, where we have more domains, should be reduced just by the fact that we kind of randomly shuffle particles from different domains that are not correlated. So in this case, mean PT will be smaller in A, but also epsilon P will be smaller. So we expect a positive correlation between those. And this is again, actually what we also find in the calculation of this. Now the question is which one survives? And what we find is that depends on the multiplicity. So if we go to high multiplicity, the geometry survives just like we would have expected from what we've seen before. But if we go down in multiplicity, actually the final result, which is the black curve here, sort of gradually goes from the geometry dominated result to what we expected for the initial state. And so around 10 particles per unit rapidity is where this correlator actually changes sign. So it would be great if one could see that experimentally. Here's just one more test. If you just turn off the initial momentum anisotropy by removing this initial flow that comes in the IP-Glasma, we actually see exactly what we expected in a purely geometric driven system, namely that, so this dotted line here is the final result in this case where we turn off the initial state momentum anisotropy, and it lies on top of the predictor for the geometry. So this really shows this came from this initial momentum anisotropy that we had this sign change. The problem is this really detectable? It's at very low multiplicity, and non-flow can actually mimic such a signal, which has been shown in these papers. So unfortunately, there's other non-flow, right? Other non-flow effects, which are, for example, in Pythia or so. And that's an issue. Unfortunately, we have to go to these low multiplicities to really see this, and we might not be able to. I'm running out of time. So I just want to briefly say, well, we should go beyond boost invariance. This can be done by including the small x evolution. Protons can evolve like this. They change in shape. We can then compute decorrelation and rapidity of the geometry and also of the initial momentum anisotropy. It looks like the initial momentum anisotropy actually decorrelates very quickly. That's a preliminary result. It would be unfortunate because with the rapidity gaps that are used in this row correlator analysis, it might mean that this initial state momentum anisotropy contribution would actually be very much reduced and could not contribute as much as we were hoping. But this is something we still need to understand better if this decorrelation is really true. But I want to go and summarize since we're running out of time. So I've shown you that the boost invariant hybrid model with IP-Glasma initial state and these subnucleon fluctuations can really describe the bulk properties in a wide range of systems very well. Different models and different Bayesian analyses actually disagree on the nucleon size. And so including this correlation of mean transverse momentum and elliptic flow could help to really better constrain the models and individually constrain the shear viscosity as well as the nucleon size. These large rapidity gaps that were used are a problem when we want to compare with boost invariant calculations, especially in the small systems. So we should really do better and, for example, extend the CGC discussion by using GymWork evolution to different rapidities. What I haven't had time to cover, even though I said it in my abstract, is that we can also go to fully 3D simulations with a different initial state, which also includes baryon densities, etc., which we had discussed in a 3D in a 3D string model, which then feeds the initial T mu into the hydrodynamics with a source term fully dynamically. I have this in my slides. I will put them up so you can have a look at this, but I won't have time to discuss it. But with that, I just want to mention all these codes that I discussed are public. You can download them, you can play with them. Some of them have a good documentation, some don't so much, but feel free to play with those. And with that, thank you very much.
Okay, thanks a lot, Bjoern, for this very nice and interesting talk. So I already see some of the question in chats and also hand raised. So maybe we have some time for the discussion. So let me ask first Neil Kamal. Do you want to ask your question? Neil Kamal.
Hello, sir. That was a really nice work, I must say. I mean, it really motivated me that lots of work has already been done in this field. And okay, so my question is, yes, exactly in this slide. So I see that in IP-Glasma, the energy density is pretty high. Is there any particular reason behind it?
Yeah, so one reason is this is a fairly early time in the IP-Glasma, so it's at 0.1. Usually we switch at 0.4. So you will have some, you will have, of course, this kind of 1 over tau like drop of the energy density. And it also depends, you see all these different models have somewhat different energies actually. And it depends on what kind of volume work will happen later. So it depends on what kind of, if they have a free streaming phase where you don't really have a volume work, and it depends on the transport coefficients in the hydro later on. So if you have more volume work, you will dissipate that energy. It will go into the transverse, or it will go in the longitudinal direction, right? And you will lose it in the mean PT, for example, more or less depending on the details of the hydro phase as well. And so these end up all having somewhat different initial energy densities, even though, or different initial energies, even though they kind of all describe the multiplicity distributions in the end. And that's because they all have kind of a different amount of volume work that kind of dissipates things into the longitudinal direction.
Okay, thank you. I would like to ask another question, if you allow me. Okay, so I wanted to know that this V2 that comes from initial special anisotropy and transport mechanism and also hydrogenization. So could you please comment if we just ignore the initial special anisotropy, then how much contribution is coming from transport and hydrogenization to V2?
You mean from the transport compared to the hydrodynamics?
Yes.
Or, I see. Well, I mean, when we switch to transport, we're already at pretty low energy densities. So not much interaction happens in our UrQMD transport phase. So in the hadronic transport, really, I think the buildup, any more buildup of V2 is negligible in our case. Right.
Okay, so initial, so all the V2 that is coming at the later stage, it is due to the initial energy density and the special anisotropy.
Yeah, well, that would be the case anyways. Or are you referring to sort of non-flow contributions that come from resonance decays, etc.? So there may be several things in the head. So in the hadronic stage, you have some rescattering, which could produce some more V2, but it's very, very rare because you have very few scatterings. The other thing would be you have some momentum correlations because of, we have resonance decay. So if one resonance decays into two particles, they will be correlated just by momentum conservation. But this is something we remove. And that the experiments also try to remove by using either rapidity gaps or other subtraction, right? So this is negligible in these final results because it's either removed or in our case, it's not there because of the way we're averaging over events as well.
Okay, thank you, sir. Thank you.
Okay.
Okay, so next question by Devjani. Can you say?
Yes, thank you very much for this nice presentation. So I have a question on slide number 21, I think. 21.
Sorry, okay, yeah.
Yes, so here you mentioned that JETSCAPE is the initial stage predictor. So I'd like to ask that what are the special features are there in JETSCAPE so that we called it initial stage predictor. So why this is so?
Oh, okay. Now this I think is a bit misleading. So JETSCAPE would have both in principle. So JETSCAPE can compute the final state correlator of the final V2 with the final mean PT. But what's shown here, that's just a choice of us, what we show here. We showed the initial state predictor from the JETSCAPE calculation. So that means instead of using V2 here, we use epsilon 2. And instead of mean PT, we use sort of a mean entropy density. So an average entropy density, which is a good representation of what the final mean PT will be. So it just means that this red curve here is not computed after the hydro, but before the hydro. It's a predictor. I'm actually not sure why we chose to do this. I have to ask Giuliano why he chose this curve, but it's just a choice. So it's nothing special about JETSCAPE. So we could have as well shown the JETSCAPE final result, but I think we didn't have that at the time. JETSCAPE hadn't provided that yet. And that's why we chose this predictor. So it's just like what I had kind of here in the later plots when I showed these curves. So this would be, this green curve was a predictor computed from the initial state, and then the corresponding final result would be this blue curve. So for this quantity, it would be very similar. But yeah, this is just what this means. It's just the quantity we chose to plot there for JETSCAPE. I think their final result looks very close to this initial state predictor.
Okay, thank you.
Okay, so next I see a hand raised by Noor. Noor, could you please ask?
Thank you. Can you hear me? Yeah. Hello, can you hear me?
Oh yeah, now I can. Okay.
Yeah. So actually, I have a question on the slide. So this rho V2 square and this mean transfer, is it kind of like a Pearson correlation coefficient, right?
Yes.
Yeah, so here different model gives a different value. So it is depend on this hydrodynamic code or treatments of hadronic interactions in these models, or it is kind of like a different initial energy density profile, which basically depend on geometric effect. Is it because of this or any other thing? I mean, why they are different for different models?
You mean the models shown in this particular plot or in general?
Yeah. So here they use the JETSCAPE
Right.
in these different models.
Yeah.
So it is. I think it's not primarily depend on this treatment of the different hadron interactions. I think it is because of some energy density profile, right?
Yes, exactly. And that's actually the point of this study. So we had noticed, if you look at JETSCAPE or our result, and so they were giving very different results for this correlator. And the question was why, right? And so what we tried to find out in this paper here with Giuliano and Chun was what's the reason for that. So, and here you see that if we change this initial energy density distribution, like you say, so we're increasing this W hotspot size, then we see large differences, right, in this correlator, even sign changes or not. But if we change the viscosity, so the transport properties, we don't see much of a change. So that's between gray and yellow here. In particular for V3, you see there's not much difference between very different viscosities. Very large bulk viscosity in the yellow, in the gray, and very zero bulk viscosity in the yellow, and they lie on top of each other. So this tells you that this correlator is really sensitive to the initial state geometry, but very weakly sensitive to the final state, which is great because then we can use it to constrain both of them separately.
So that's why it is this weakly centrally dependence also, right?
I'm sorry, come again?
It is not depend on the centrality, weakly depend on the centrality.
Yeah, the V3 one is very weakly dependent on centrality. And yeah, I mean, the V2 one as well, if you look at the data, right, it's very flat. It is also kind of flat in our case, we overshoot the data. So the blue one is our standard result. And so we overestimating the data. And then we kind of go down. I don't know what the data will do if you went further. Unfortunately, there's no data.
For this right plot, so after 50% centrality, so in this IP-Glasma with UrQMD music follows the opposite trend than the data, right? So here this IP-Glasma use this initial momentum anisotropy included or it is excluded?
It is included. I don't think it matters very much yet because this is a lead collision and we're not that peripheral yet. So if you look at our little other Pearson coefficient, right? If you, I don't know where 60% is, but I think it's around here or so. there, maybe we can count, it's somewhere here. You see the initial state anisotropy only has a small contribution there. So I don't think it will matter much.
Okay. Thank you. Yeah.
Mm. It's
Okay.
all just geometry.
Okay, so I see one or two hands raised, but maybe just let me also ask one question. So, Bjoern, you mentioned about the hotspot. So, after the evolution and hadronization, how do the hotspot appear as a soft bulk, or do they also appear as a hard or semi-hard objects, as semi-hard objects after the hadronization?
After hadronization, well, after hadronization, they're all gone, right? In the sense they're converted to, yeah. So I guess your question is, do I see is in the PT distribution of particles, right?
Yes, correct.
Yeah.
Because in the high multiplicity events, we also see that jet cross sections goes up. So I was just trying to see whether hot spots can contribute to explaining that kind of feature or not at all.
They will lead to a harder spectrum, definitely. That's why we need a larger bulk viscosity to kind of to avoid this again, right? Because the bulk viscosity kind of is working against this volume expansion, right? So the small hotspots will give you a greater push because of larger pressure gradients. So that increases the mean PT, as you say. But then in order to describe the spectra correctly, at least up to, the 3, 4, 5, maybe 3 GeV in PT, I would say, we need the larger bulk viscosity to kind of reduce this again, because the small hotspots will actually do too much. In regards to even larger PT, I don't think we can say much. I think just the hydro by itself is not describing that well enough. So I don't think we can really learn from just that model whether the hotspots have what kind of effect the hotspots have at the higher PT. Yeah, because I think the hydro is just not describing it well enough. It's too dilute in that regime, in a sense, for the hydro to be reliable. So we usually stop at like 3 GeV, and beyond that we don't really ask questions. Yeah.
Okay, thank you. So now Tribhuvan.
Yes, so thank you, Professor Schenke. I have one question that my question is related to a framework, basically. The framework that you are using a hadronic afterburner after the hydroparticularization, but initially, I mean, before 5-6 years, it was not been done, only Cooper 5 particularization and then decay all of a sudden. But what is the motivation behind it to tweak this hadronic afterburner in the calculation? And I mean, even in large energy, we are taking it, and at which energy it will be important, and if we will not include it, what kind of problem we're going to face?
Okay, yeah, that's a good question. I don't think I have a plot, and I would say if you're just interested in pions, or if you include all charged hadrons, which are mostly pions, it does not have a too large effect. It's mainly important if you're interested in identified particles, in particular protons and antiprotons. For those, it makes a difference. So it will affect your spectra of protons. It will affect the V2 of protons. And that's mainly because, well, you have some annihilation effects in the rescattering. You have some other effects. You have some additional push maybe that the protons feel from some residual interactions with the pions, yes, right? Like a pion wind, etc.
Yes,
so you will see some difference in the protons mainly. Sorry,
yes, I have shown those plots that how that hadronic how that V2 is changing, but one can manage that by tuning the shear viscosity over entropy density ratio. It's not necessary, I mean, to include that hadronic transport phase. So, I mean, basically, what will be wrong if you will not include even in low energies also?
I mean, it's definitely more important than the low energies. I think it's a detail. I think if I showed you these plots here without the hadronic afterburner, you would not really see a difference. As I said, so for the charged hadrons overall, you wouldn't see a difference. I think if you're interested in the details of the protons, it still makes some small difference. But yeah, I don't think it's huge at the high energies either. I think I agree with that. But you know, we included to be, well, as doing as well as we can, even at the high energies, even if it's a small correction.
Yes, thank you. So another question I have, can I ask right now?
Yeah, sure, up to the chair. But yeah, go ahead.
Yeah, maybe we can just take one more question and then.
Okay, okay.
If it is okay, Bjoern, for you, it is okay?
Oh yeah,
Because,
yeah.
Oh, then we have no problem.
I'm awake now.
Okay, then fine. Then we can take up maybe few more questions if it is okay with you.
Sure.
Okay.
Yeah, in slide 20, in slide 24, the uranium V2 at ultracentral collision, that has not been shown there for the theoretical calculation. I mean, the simulation results.
You mean here?
Yes.
Yeah,
So
I think we're running.
Explaining that part.
I think we're running out of statistics because, you know, this is on the tail of the multiplicity distribution, and we don't have enough events there, I think, to really go into that tail with confidence, right? So I think we would have to just, because what we do is we really run minimum bias events with the hydro. So we run really every event through the hydro, and then we bin in the end really in real hadron multiplicities and select and here I think we just run out of statistics because it's in the tail of the distribution.
That non-monotonic structure may be because of the nuclear deformation, probably. Am I right?
Yeah, I think so. Yes. I mean, this is right. I think, you know, we could trigger on high multiplicities, right, and not just run everything, and we could get there. I believe, I mean, we looked at this in a different paper with some older version of the whole framework. And we kind of looked at this more differentially also. I think, yes, I think it's the effect of the deformation in the uranium. Because now this is a mix of, you know, you have these tip and you have these side or whatever they call it, collisions, right, where you have the different orientations. And you will also, if you look more differentially in multiplicity there and the very, very central collisions, you can see this correlation somehow between the V2 and the residual multiplicity difference, right? And then you can really distinguish, I think, does it come from this orientation of the nuclei or this orientation, right? Where you have sort of the cigar shape colliding like this or colliding like this. I think this is where this comes from. Now, this is a mix of the two, right? But yeah, I think this is what this is. But in this calculation, because of the way we did it, we didn't have enough statistics at that point.
Okay, thank you.
Okay, so we take two quick questions, one by Captain Rituras and then next by Priyanshi. Please go ahead.
Yeah, hello, sir. So in your slide 9, you said that you took tau equal to 0.4 FM. So I want to know, how did you choose it? Means you have chosen it. So my point is asking that you are taking any transition from Glasma state to the thermalized QGP. So you know that at this point, Glasma will be thermalized. So this is how you have obtained this tau, or is there any other way?
Yeah, I wish it was thermalized. Unfortunately, it doesn't really thermalize. It is because in particular in this, as I said before, in this 2+1D simulation that we do here, so we really have a boost invariant calculation here. It won't thermalize. So what will happen is you start with a negative longitudinal pressure, and that will go to 0 eventually. By 0.4 Fermi, it's about 0. And the transverse pressure will still be positive, but they won't be the same, right? So if you, on thermalization, you need at least isotropization of the pressures, right? So you would think they're all 1/3 or something like that, right? Or 2/3 for the transverse pressure. But that doesn't happen actually. So at this point, when we switch, we do have a pressure anisotropy still, which we do absorb in the hydro in terms of the shear and bulk viscous corrections. Those will you know, so I said we're matching exactly, and in order to match exactly, you need some effective bulk viscous and also the shear viscous corrections to have that. So even if I waited until 1 or 2 Fermi, it will not be isotropic in this system.
Okay.
Yeah, and
Okay,
so the
means
choice.
there is,
Yeah.
yeah. So there is no way to obtain that this tau actually.
There's no way to obtain it. You can
Yeah.
you can try and fit, right? You can try and choose sort of one that works best. It's just like with the other models that use sort of a free streaming phase. It's kind of like that, because if you keep running the IP-Glasma, it's just free streaming, because the interactions of these gluon fields will go down because it becomes too dilute, and then it's just a free streaming. So it's just like how long do you do the free streaming versus the hydro, and that's the same choice here essentially. And 0.4 is kind of where at least the longitudinal pressure is no longer negative, but is 0 at least. And so at this point, we feel more confident to switch than even earlier.
Okay, thank you. Yeah, so one more question. So can we use this music code for a small system like PP collisions at LSC?
Yeah, well, I have, but yeah, it's pushing it a bit. But I think, you know, one under the assumption that things are still strongly interacting enough, one can use it. I mean, with the current setup, it doesn't work very well. So this is what I showed here. So this is PP 13 TeV. You know, the multiplicities go up pretty high, you know, close to what the PLED has here, right? And so why not, right? If you use it for PLED, you can use it for PP.
Okay, so
but that's again, I think it's just more sensitive even to the details of the geometry of the proton, and that's, I think, why it doesn't work. But other reasons may be that there's more non-flow in there that we don't have, etc. So I think you're missing some physics also probably in PP if you just do some hydro, right?
Yeah. Okay, thank you.
Okay, so last quick question by Priyansi.
Yeah, hello. Can you hear me?
Yes.
Yeah, so I just had 2 small questions. So in the first few slides, there was an equation in which you had considered some correction factors, viscosity correction factors. So may I ask which viscosity would actually dominate in that correction?
You mean between shear and bulk viscosity?
Yeah.
It depends on which quantity. So so the bulk viscosity is something that works against this volume expansion, right? As I mentioned briefly. So if you have a system that's just expanding and it's trying to push outwards, the bulk viscosity is trying to avoid that. So bulk viscosity will affect a lot the mean transverse momentum. Shear viscosity, on the other hand, right? It tries to prevent sort of different layers to move at different velocities, like doing this shear motion. So shear viscosity is trying to get neighboring layers to move at the same speed. So this explains why shear viscosity will make things more isotropic, right? So if you have a layer moving fast in this direction and a layer moving more slowly in this direction, the shear viscosity will try to make these 2 velocities more equal. And so that reduces the VNs, right? In particular, it reduces the higher order VNs. So if you're interested in this anisotropic, in this momentum anisotropy, like V2, V3, and even the particularly higher ones, the shear viscosity has the larger effect. But if you're interested in mean PT, so just this overall expansion, then the bulk viscosity will have the larger effect. So it depends on the observable, which one is more important. Does that answer your question?
Okay, and just, yeah, it really does. And just one another question. So we mostly see you trying to predict the V2 was like say PT. But what if we try to model the V2 by the V2 or V3 by the corresponding eccentricity? How will the model predict or behave for that?
Yeah, so the predictors, I don't have a plot, I think. So the predictors for V2, just using eccentricity, they are pretty good. so usually it's, you know, as you may know, you have this linear and non-linear contributions in the hydro, and for V2 you have some mixing in, right? So if you have epsilon2, you typically also need like epsilon 4, etc., maybe epsilon 3 even. So some for those guys, you will always have some mixing, but usually epsilon 2 is already a pretty good predictor for V2, which is kind of shown in this one plot I had for these things. So right, for if you look at this is a more complicated thing, right? But it has just epsilon 2 as a predictor for V2, and the final result is very close. This, of course, mixes in the mean PT and all this, so it's a bit more complicated. But if you did the same exercise for epsilon 2 and V2 for the most centralities, it works pretty well. If you want to compute V4, right, and you go to peripheral events, the epsilon 2 will matter, right? So you will have an epsilon 2 squared contribution to V4. So let me recap a bit. So for the lower harmonics, V2 and V3, this linear relation is pretty good. As you go higher, you will have mixing in from epsilon 2 squared and things like this. So it gets worse. Yeah, so usually these predictors work pretty well, and people have worked on, you know, getting better and better predictors which have more complicated structures and all these nonlinear things in there. And so with those, I think one does pretty well and doesn't even have to run the hydrogen anymore, right? Once you have confirmed that they work very well. Yeah.
Okay. Thank you.
Okay, so I think now, so I think we had a good discussion, a good talk followed by a good discussion. So Bjoern, I thanks you again for your.
Thank you.
So we exceeded, we exceeded your 1 hour. I hope this is fine.
Oh yeah, with me as well, no problem. If you are okay, then everything's good.
Okay, then with this we close today's session and see you sometime in person, maybe somewhere in Quark-Meter or somewhere else. I do not know.
Yeah, I hope so. Let's see how if we can travel to Poland. All right. Thank you.
Okay. Thank you everyone for joining.